This slide shows the results of water and polymer flooding experiments carried out on a single-layer sandbag model. In this experiment, we are displacing 420 centipoise oil from a sandbag that was tightly packed into a cylinder, 4.3 centimeters in diameter and 8.6 centimeters long. And of course, before water flooding, the sand was saturated with oil. When we injected 1 pore volume of water, we recovered about 30% of the oil. The dashed line here shows our projection, how much oil we would have recovered if we had continued water flooding beyond 1 pore volume. According to the trend, it would have reached around 42%. But instead of continuing with water, we switched to polymer flooding right after injecting 1 pore volume of water. The polymer solution we used had a viscosity roughly 11 to 12 times higher than that of water. As you can see, this increase in the viscosity of the displacing fluid significantly accelerated oil displacement, resulting in 70% oil recovery from the model. Compare this to the 42% projected based on water flooding alone. Even in a simple single-layer homogeneous reservoir, polymer flooding can significantly improve oil recovery. The increase of the displacing fluid's viscosity reduces mobility ratio, which in turn eliminates viscose fingering. Keep in mind that this was a constant flow experiment, meaning that the injection velocities of both water and polymer solution were equal. So a question may arise: how could we decrease the mobility factor if the velocities of water and polymer were the same? Let's think about it. These are the formulas for the velocity of water and polymer in porous media. We can safely assume that the permeabilities of our sand to both water and polymer are equal. However, the viscosity of the polymer is much higher than that of water. This is why the pressure drop across the model during polymer injection is also higher than what we observed during water flooding. These pressure drops apply not only to the injected fluid, water or polymer, but also to the oil present in the model. In this particular experiment, the higher pressure drop during polymer flooding forced the mobile oil to flow faster, resulting in a higher oil velocity compared to that during water flooding. Yes, the velocities of the displacing fluids, water and polymer, remained equal. However, the ratio between the velocities of the displacing and displaced fluids is lower in the case of polymer flooding. If we express these velocities using Darcy's law, the pressure gradients cancel out since they are the same for both water and oil during water flooding, and for polymer and oil during polymer flooding. As a result, we are left with the ratios of the permeabilities and viscosities of the fluids, known as fluid mobility. So even in a constant flow experiment, switching from water to polymer reduced the mobility ratio or mobility factor, which eliminated viscose fingering and accelerated oil displacement. We should also note that laboratory experiments sometimes tend to overestimate the oil recovery factor achieved through polymer flooding. But perhaps we will discuss that in our future lessons. For now, I believe this explanation is sufficient to understand why we observed an acceleration in oil displacement when switching from water to polymer injection in our constant flow sandbag flooding experiment.